In this video, we will continue our discussion of applications of definite integrals, specifically looking at volumes using cross sections. And in this case, when our slices of our solids look like cylindrical discs. So in this next example, we will consider the solid generated when a region is revolved around an axis. And when we slice a solid that's generated by revolution about an axis, the slices will resemble thin cylindrical discs or washers. And I've got a cylindrical disc and a washer pictured here. If I take a look at the cylindrical disc, and if I want to find the volume of that cylindrical disc, just as before, it's always the area of the base times the height, or times the width. So in this case, it's very much like our prism that we looked at in our first video. In this case, the base is a circle, where we've got a radius. So we have pi r squared is the area of the base times our height. When we consider a washer, this also would be a circle, and it has radius, which we'll consider r sub o for an outer radius. And then if I go in and I remove that center circle, it also is a circle and it has a smaller radius. We'll call it the inner radius, r sub I. The volume of those washers is found by calculating the difference in the areas of the circles multiplying by the height. So let's consider an example where we find the volume using cylindrical discs. Let's consider the region R bounded by the graphs of y equals 2 times the square root of x, x equals 1, and the x-axis. Suppose this region R is revolved about the line x equals 1. Find the volume of the resulting solid. Again, I'd like you to pause the video and I want you to sketch the two-dimensional region that's been described as well as the resulting solid. So here's the region that you should have sketched. We've got y equals 2 times the square root of x, the x-axis, and the line x equals 1. We want to revolve this region about the line x equals 1. So when I graph the three-dimensional solid that results, I'm going to consider the fact that this will go over here. We'll make a circular base, and I can think of kind of a circular regions, circular cross sections at any slice that is perpendicular to that line x equals 1. So in many ways, it might look sort of like a chocolate Hershey kiss. We're going to proceed as we did before. We're going to partition the interval. We're going to find the volume of the kth slice. We're going to sum the volumes of the slices using a Riemann sum, and then we're going to take the limit of the Riemann sum as the norm of the partition goes to 0 to develop our definite integral. So first, let's consider the partition. Well, what interval do we partition? Well, the fact that the cross sections are always taken perpendicular to the axis of the revolution means that we're going to make slices perpendicular to the y-axis. So we actually need to partition the interval from 0 to 2 along the y-axis. So our partition will be p equals y sub 0, y sub 1, y sub 2, up through y sub k minus 1, y sub k, up through y sub n. And as before, this is y sub 0 is 0, and y sub n is 2. We're going from 0 to 2. And you can see the partition there, how we've partitioned the region using thin rectangles. So here's a rectangle. We would have another, here's our first rectangle, here's our second rectangle, here is our kth rectangle. Okay. Now, given the fact that we partitioned along the y-axis, means that we need to have our equation as an x equals y equation, because whatever interval we partition determines the variable with which we integrate when we develop the definite integral. So I've solved y equals 2 times the square root of x to be x equals y squared over 4. So again, I'm going to take a look at this two-dimensional perspective, but now I'm going to look at one rectangle, the kth rectangle, that gets revolved around the line x equals 1, giving me a cylindrical disc. So as I think about this rectangle being rotated about the line x equals 1, it's going to be a very flat disc. And I'm going to extract that and pull that out over here. So here is the center of that disc, and that's along the line x equals 1. And I can see that the height of this cylindrical disc, or the thickness of it, is based on the partition points y sub k minus 1 and y sub k. So the difference in those partition points will give me the thickness of the disc. The radius, because I know this top surface here is a circle, so I know I need to find the area of that circle. Well, the radius of that disc comes from the line x equals 1 to the x value based on the curve. Okay. Now, always subtracting, since radius is a value or a distance, we always need to take the greater minus the lesser. So in this case, we're going to take the right minus the left. So if I've got x equals 1 for that center axis, and x equals y sub k squared over 4, I'm going to calculate my radius as 1 minus y sub k squared over 4. That'll be my kth radius that I use for the cross-sectional area of this slice. So putting those pieces together, I've got the volume of the kth slice is delta v sub k, which we calculate as using the area of the kth cross-section times the width. I know that the cross-section is a circle, so it has area pi r squared, so it's going to be pi times the radius squared, and the radius we determined to be that right value, which is x equals 1, minus the left value, which came from the curve, so y sub k squared over 4. I calculate that difference. That radius gets squared, and I multiply times delta y sub k, because that's the width of my slice. And now to find the volume of the solid, by approximating that using the sum of the slices, I get sum going from 1 to an n of delta v sub k, which I get k equals 1 to n, the sum of pi times 1 minus y sub k squared over 4, quantity squared, that's my pi r squared times my width, or my thickness. I let the norm of the partition go to 0, and so I've got pi times 1 minus y squared over 4, quantity squared. I'm integrating with respect to y, and I partitioned along the y-axis on the interval from 0 to 2. So those become my limits of integration. And I get pi times the definite integral from 0 to 2 of the quantity 1 minus y squared over 2 plus y to the 4th over 16. Integrating, I get pi times y minus y cubed over 6 plus y to the 5th over 80, and I evaluate that from 0 to 2, and I get 16 pi over 15 cubic units.